I got my PhD in 1984 working on the baroclinic instability problem under Wesley Scheer. Charney solved the problem, but Charney didn't look at the Eastleigh Scheer instability, but he speculated about the same, like in his paper. Then I read Shukla's paper about the monsoon depression, the baroclinic, barotropic, and cumulus convection. I was pretty interested, so I wrote a letter to him for a postdoctoral positions. But I got a reply 3 months later, when I was moved to GFDL already. So regrettably, I not being able, early member of COLA. But anyway, this is going to be a discussion of to what extent this monsoon rainfall can be predicted on the decadal timescale, and what is a potential physical basis for thinking this problem. Collaborate with many papers, so including Peter here. To think about the decadal variability, we have to start to think in the global picture, the global scales first. So if we use precipitation characteristics to quantify the monsoon domain, this green area is the regions, including South Asia, East Asia, North Africa, Central America, Venezuela, and Southern Hemisphere, Southern America, Southern Africa, and Australia monsoon regions. You see the yellow regions are the dry, semi-arid or arid regions. Those ITCZs go through this monsoon trough regions, about 3/4 of ITCZ basically embedded in that monsoon regions. And this Northern Hemisphere monsoon has a very concentrated rainfall, about 70–80% of the rainfall, the ITCZ actually in the monsoon regions. And it drives this global circulation. This is the difference between January and July. So the upper level circulation would be just the opposite. So to summarize, I think global monsoon should be seen as a circulation system. It is an annual reversal of the global three-dimensional monsoon circulation that is accompanied by seasonal migration of the monsoon trough. So the global monsoon is really a leading mode for annual variation of the climate system, and is a defining feature of the Earth's climatology. Now, this is more generic definition, maybe also applicable even when we think about the land-ocean configuration dramatically change on the geological timescales. Most people study the variabilities, look at the regional scales. So I want to focus on this Northern Hemisphere scales because the Northern and the Southern Hemisphere is antisymmetric. They have different variabilities. Now, if you look at the year-to-year variability in the left panels, the spatial pattern is roughly uniform, and the temporal variations is related to ENSO. And if you do 3-year running mean to fill out this to suppress year-to-year variability, in the right-hand side, you see the spatial pattern is still roughly uniform, and they have increased trend in the last 30 years. Now, this figure suggests that to some extent, this Northern Hemisphere summer monsoon, if we do averaged intensity, it may be meaningful to look at interannual and decadal variabilities. On the other hand, we can also think about the circulation intensity. The monsoon heating generates this raspberry wave to the west and the equator. So therefore, if we calculate the vertical shear in these blue boxes, this is a vertical shear index corresponding to the Northern Hemisphere summer monsoon rainfall intensity. This is mostly extension of the Weber-Young type of vertical shear index. So we may have two measures of the monsoon intensity: total rainfall or average precipitation rate, and vertical shear average of the 2/3 of the global tropics between equator and the 20 north. Now, if you look at the last 30-some years since 1979, the upper panel is northern hemisphere summer monsoon precipitation change, year-to-year change, and clearly there is a interannual variability, but there is a trend. And the second panel from the top is the northern hemisphere circulation indices. It consistent with the precipitation variability in both the interannual and the trend. The third panel is northern hemisphere summer hardly circulation intensity measured by the maximum overturning circulation. The trend is a kind of similar to the monsoon, but interannual variation is not precisely. And the bottom panel is the trade wind averaged over the equatorial eastern central Pacific. So when the monsoon becomes stronger, the easterly also becomes intensified. So they are positively correlated. This easterly wind is negative, so it's going down. Actually, it's a strengthening of the easterlies. So same thing in the last 30 years, everything is coherently has an upward trend. And if you look at the northern hemisphere precipitation intensity trend, if you calculate the trend, it is about 9.5% increase per 1 degree of global warming. And this number is very large, so you may wonder whether this is related to global warming or not. Now, if we take a CMIP-5 models, we took 5, we thought is best model, use MME, and to try to determine how the model tells us. So it turns out that the northern hemisphere summer monsoon precipitation increased only 2.6% per 1 degree of global mean temperature increase. So where is the other 70% increase? It may be suggesting that it's multi-decadal variation, a part of multi-decadal variations. So to look at that further, we have to look at the longer time scale data. So we took land-only CRU data and look at the UF patterns. You see the first UF pattern still pretty much uniform. And this is from 1901, about 110 years. And you see the interannual and multi-decadal fluctuations. This does not, if you take in this 20C reconstructed data, basically they are highly correlated. And if you do, if you look at the vertical wind shear index derived from the 20C reanalysis, you can go back to 1871. And they are also highly correlated with the northern hemisphere summer monsoon land area rainfall. And in addition to interannual variations, you have those multi-decadal peak, suggests something is low frequency variations. Now, to look at how this variability linked to SST variations, this is a regressed field. And the increased northern hemisphere summer monsoon rainfall within this red curve regions is accompanied by the East Pacific Triangle region cooling and Western Pacific warming, also the North Atlantic warming and the Southern Atlantic cooling. So what does this SST patterns means to us? So if you do a UF analysis from 1870, the first UF is uniform, a sort of uniform warming. But the second UF is really characterized by the East Pacific Triangle cooling and the Western Pacific K-shape of warming. And it's dominated by the multi-decadal oscillation in the middle panel. It's more like IPO type of fluctuations and spatial patterns. The third UF is very clear, is Northern Atlantic warming and Southern Atlantic cooling. And this pattern sort of suggests the global ocean has a hemispheric asymmetric distributions. And that means that the sea level pressure could also has a hemispheric difference. and the cross-equatorial flow may be favored for the northern hemisphere summer monsoon. So we can just quantify this PC2 and PC3, think of their multi-decadal component. For the PC2, we can define new IPO index using total field, not UFs. And you take SST anomalies, averaging on the Western Pacific, the K-shaped region, minus Eastern Pacific triangle regions. You can quantify the year-to-year variability and decadal variabilities. And for the Atlantic north-south, we can define a sample index called Atlantic Dipole Multi-Decadal Oscillations. So this ADMO is just North Atlantic minus South Atlantic. Now, the ADMO, AMO, of course, they are correlated, but there are some differences between them. And for example, if you use AMO to make a detrained AMO, make a regressed global SST, you see there is a uniform warming patterns associated with that. But if you use ADMO to look at, they apparently has a strong north-south asymmetry. And we think it's more relevant to think about the hemispheric change of northern hemisphere summer monsoon. Now, this figure shows if we take these two indices and simulate the northern hemisphere summer monsoon rainfall, the upper panel in the past 110 years, you get pretty good cross-validated scale. Now, when you go down to the regional scale, the middle panel is the North Africa summer monsoon land rainfall. You still get very significant scale of 0.68. And for Asian summer monsoon land areas is further lower, but still significant. In other words, to look at the hemispheric scale of the monsoon rainfall is probably more predictable. The upper panel of this figure shows the vertical wind shear indices over the past 140 years. And again, you can simulate using these two indices with a significant scale. Now, of course, this suggests that if we want to predict monsoon rainfall, we have to be able to predict this AMO and IPO. And their mechanism has been discussed. Team also discussed this in the previous talk. I don't want to go into details, but I think the AMOC is more related to ADMO. Okay, now, suppose we take the CMIP5 decadal prediction Hancock experiment, directly look at the model's prediction scale for the northern hemisphere summer monsoon land rainfall. That is the black curve. You see there are some scales, but when you go down to Asian monsoon, Africa monsoon, the green curve, they're basically scale very low. But the scale is most come from the model capture this upward trend after 1980, as shown in the right panels. In the beginning, 1960s, this rainfall peak, the model basically missed. So if we look at the SST variabilities, most models can capture this ADMO, but IPO has a difficult. So what the problem is this IPO predictions, the model predicts the temporal evolution is fine, but the spatial pattern is very much biased. So if we throw the dirty water of the spatial pattern, replace that spatial pattern, use observed pattern, we can reconstruct the SST anomaly predicted by the model and recalculate this IPO index so that we can use model predicted SST plus empirical relationship. This empirical relationship, of course, we use anything before the initial time, 60 years of data to build this relationship, use forecast as the next 10 years, then to forecast the northern hemisphere summer monsoon rainfall. Now, this is called hybrid dynamic empirical predictions, very much similar to the two-tier approach, except we use the UF1 dominant mode in the Atlantic and the Pacific. So here is the prediction scale. The black curve in the left panel is Northern Hemisphere summer monsoon, and the green curve is North Africa. The red curve is the Asian monsoon. And all of them suggest there is a possibility that you can predict 6 to 9 years with a useful scale. The red panel suggests that they do capture the peak in the early 1960s, so they capture this multi-decade oscillation. So I want to stop here. Thank you.
So just for confirmation, you're saying that during the last 20 or 30 years, when we had this strong increase in the rainfall, we're getting a contribution both from the El Nino going to the negative and the Atlantic also. They've been pulling in the same direction and giving a strong change in the monsoon.
Yeah, I think probably most contribute to that.
Okay, well, let's thank all our speakers.